And next, we have Mr. Zakaria Faddi, also from. Oh, Mr. Zakaria Faddi, also from UMass Dartmouth.
Thank you for that introduction. So when we talk about machine learning, everybody wants to play with machine learning. It's the new kid on the block. Everybody wants to implement it in their system. But how can we make sure that it is reliable and it is functioning properly? So that's why we try to use very well-established software reliability methods and resilience models to the machine learning systems. So what is software reliability? It's the ability of software to perform its intended function without failure for a specified period of time. And what is software resilience? It's the ability of software to recover from a failure and continue to operate. So when we deploy those models in real world scenarios, it requires that these models can adapt and change conditions and handle uncertainties effectively. This ability to be resilient is very critical, and especially when dealing with complex tasks. These ML models must be able to perform well, even when faced with incomplete or ambiguous systems. And without solutions to address these challenges, the reliability of these ML models will remain uncertain, leaving many industries vulnerable to these potential failures. A lot of past research have proposed enhanced techniques to enhance the defense of the ML models, but none have used well-established failure models to assess those, and that's what we propose. So what is our contribution? We apply software reliability growth models, aka SRGMs, to characterize defect discovery in the ML-enabled systems. And we apply resilience models, which my colleague has showed earlier, to predict the ML systems, and we show their applicability. So what I'm trying to do with this research is to show you how you can apply these to your specific needs and to your specific systems. So we'll be showing an exemplary system that I developed, but it's very basic, but these can be applied to anything or any system that you might be using. So here's a small introduction and background. Utilized a CNN model, which is a deep learning model used for image classification and object recognition tasks. And to create attacks on that system to show the degradation of the performance, we generated adversarial attacks, which were designed to deceive the target model. And we also incorporated adversarial examples into the training data set using adaptive adversarial training, which will help the system recover or show the return to optimal the performance. And so for the reliability and resilience models, we use non-homogeneous Poisson process, software reliability growth models, and we use discrete cost proportional hazard models. So what is the difference between the two? The NHP SRGM models are statistical models that describe the number of failures or defects in a software system over time, while the discrete cost proportional hazard models they characterize failures and defect discovery as a function of test activities and related software metrics. So the software metrics part is the important part, because we can also refer to that as covariates, where both the discrete cost proportional hazard models and the resilience systems use. So this is an architecture of the system that I built, but again, this can be applied to your specific needs, and you can collect specific data based on your system. So we trained the model using clean labeled data, which shows that it's trained and it performs to your nominal preferences. But after the model has been deployed, we introduce attacks that it hasn't seen before. And why do we do that? Because we want to show the degradation. Say, for example, you have an application online that hasn't seen a specific cyber attack before, and that attack happens. What happens? Does it just fail and crash, or does it return and learn from that and goes back to proper functioning? So once we collect that data, we perform iterative retraining to train the model on that new data. So we don't go ahead and just collect the data right away. There's a certain amount of time before we do that, and then we perform the iterative retraining. So this becomes like a min-max game between the two, where the attacker tries to maximize the loss, and the retraining tries to minimize them. This is an example of data collection that I collected for the HPP SRGM models. We collect failure time, and for the discrete cost proportional hazard models and resilience models, we collected failure counts along with the covariates that I mentioned. These can range again based on your specific system. You can collect more, you can collect less, but these are just examples. Some of which is how much amount of noise I added to the image, the percentage of each attack, the memory that was used by the adaptive initial training. And I will show you how you can use this data with the model that we applied. So this is the HPP SRGM model. How can you use it? How can it benefit you? So on your left side, you can identify a trend in defect discovery to identify bottleneck and resolution process. So these are specific models that can characterize the trend based on the failure count. And on the right-hand side, you can see that this is a reliability plot, which will help you identify trends in failure rate to identify the effectiveness of corrective actions. So the actions that you take to help your model, how effective are they? Here we use the discrete cost proportional hazard model, which uses covariates. The covariates are the data set that you collect. So here they are a lot better than the previous ones because we have more data to work with and we learn more from that. This is the resilience model, which you can see here. There's a sharp trend where the introduction of attacks happens and there's a degradation. Does it recover? Yes, because we perform the adaptive initial training and the models are very effective at doing that. And here's some of your conclusion. We developed a data collection technique to apply traditional HPP SRGM models, specifically characterize the deterioration and recovery of ML-based models. Future research could use advanced statistical techniques, application to cyber-physical systems, or application to pre-existing ML-based systems. Thank you. This is an acknowledgement.